Dear students, let's start from where we left. This is going to be the third lecture of Fourier analysis. MTH803 is the code, and let's start from where we left. That is the convergence of Fourier series. Now, Fourier series, as you already know, is the series of the form 1 by 2 a naught plus summation an. Let me call it ak. K runs from 1 to infinity cos of kx plus b sub k sine of kx, right? Where f is, we're given an f which is a Lebesgue integrable function over minus pi to pi, and what are these coefficients. Now I don't need to repeat it again and again. Okay, now in order to see when a series of functions, a series converges, we have to look at the nth partial sums. So nth partial sum of this series would be s sub n of x is a naught by 2 plus summation k runs from 1 to n a sub k cos kx plus b sub k sine kx. So now we know that what is ak, a0 and everything else. Now a0 we know is 1 by pi minus pi to pi f of x dx, and similarly for k greater than equal to 1, ak is equal to 1 by pi minus pi to pi fx cos kx dx, and b sub k is the same thing except in place of cos we've got sine kx dx. If we substitute it back, we want to write it in a more compact form or nth partial sum, so we can look when it converges. We can see under what conditions would it converge. So I can write it as 1 by a0. In place of a0 I can substitute 1 by pi integral from minus pi to pi fx dx, and similarly in place of summation k runs from 1 to n, in place of ak I can write 1 by pi integral minus pi to pi. Now I want let me write it as ak, that would be ft cos kt of course dt, and then multiplied by cos kx plus summation k runs k, one and the same thing, 1 by pi, that would be our bk, minus pi to pi f of t sine kt dt cos kx. Now I just used a different letter for this variable because I already have an x here, right? So the dummy variable, the variable of integration is t, and similarly I make the same change here. It doesn't matter, it's a dummy in any case, right? So I can write it in a compact form as 1 by pi. Now since I see ft is here, ft is here, and ft is here, and we have a finite sum, so we can put it under the single integral. So I can write it like minus pi to pi, I take ft out, and since I have 1 by 2 here, so I can write 1 by 2, then I would have, what would I have? I would have ft is out, pi is out, so it would be summation k runs from 1 to n cos kt cos kx, right? Of course it has to be a plus here, and plus sine kt sine kx, and of course our integration is with respect to t. Okay, now we use the formula for this. We know that cos a cos b plus sin a sin b is basically cos a minus b, so then it becomes 1 by pi integral minus pi to pi ft into 1 by 2 plus summation k runs from 1 to n cos of k x minus t dt, and which I write in a slightly more compact form as 1 by pi minus pi to pi f of t multiplied by d sub n of x minus t dt. Okay, so that will be my nth partial sum of a Fourier series, and so in a compact form, where of course I have substituted that dn of x minus t is equal to 1 by 2 plus summation k runs from 1 to n cos of k into x minus t. Or in other words, I could think of dnt as 1 by 2 as another function as 1 by 2 plus summation k runs from 1 to n cos of kt. This is called Dirichlet's kernel. So that would be now our compact form for the nth partial sum of a Fourier series. Okay, here it is. Okay, but we can also write this in a in another way. So because now this dn of t is equal to 1 by 2 plus summation k runs from 1 to n cos of kt, I can use the certain trigonometric relations, like I can just start from twice sine x by 2 into cos of x using trigonometric formula would be sine of x plus x by 2 minus sine of x minus x by 2, and then twice sine x by 2 as it is into cos of 2x would be sine of 2x plus x by 2 minus sine of 2x minus x by 2, and you can go on and on. Then twice sine x by 2 cos nx up to n, I would get sine of nx plus x by 2 minus sine of nx minus x by 2. We're just using the formula that twice sine a cos b is sine a plus b minus sine a minus b. Now if we sum this from the left hand side and the right hand side, we see that twice sine x by 2 is common. So left hand side would be twice sine x by 2 into summation k runs from 1 to n cos of kx, and on the right hand side we see that x plus x by 2 is the same thing as 2x minus x by 2. So these terms would cancel diagonally, and we will be only left with two terms, and those would be sine of nx plus x by 2 minus, and this term sine of x by 2. Okay, now this can be written as sine of n plus 1 by 2 times x minus sine of x by 2, and if I divide both sides by this factor, I get summation k runs from 1 to n cos kx is equal to it would be sine of n plus 1 by 2 into x divided by twice sine x by 2, and here I would get minus 1 by 2. So I have 1 by 2 plus summation k runs from 1 to n cos of kx can be written as sine of n plus 1 by 2x divided by twice sine of x by 2, right? Okay, so but this is, if I look at this expression and this expression, there is only just one change of it's just a change of variable, in place of x we have t, so I can say dn of t can be written as, looking at this formula, this is actually sine of n plus 1 by 2 times t divided by twice sine t by 2. We just note it down here. Now it tells us something about, now it also tells us something about this Dirichlet's kernel, which should have been rather obvious, that this Dirichlet's kernel is a periodic function because it is sine divided by sine. So if you it's a function of period 2 pi. That's easily verifiable. Okay, moving ahead. If I now just make a change of variable by putting u equal to, in this integral, in the star integral, putting u equal to x minus t, so that t is equal to x minus u, and making the necessary substitutions, when of course t is equal to minus pi, u would be x plus pi. So you would actually get, by substitution, Sn of x equal to 1 by pi x minus pi. Now this is a more useful expression for our nth partial sum for this Fourier series. So I can write it as f of x minus u dn of u du. So we are going to use it, but here there is a little problem here, a subtle problem. You know, initially our function is basically defined on the interval minus pi to pi, right? But here, as we see, once you fix u in this interval and let x, rather fix x in this interval and let u change over whole of interval, then this x minus u would go outside the interval. You take x closer to, say, pi or to minus pi, and then you subtract pi or pi by 2, which you can because u ranges over this interval, then our function wouldn't be defined in this case, if the function initially was only defined for minus pi to pi in closed interval. But we can overcome that by making our function, by extending the definition of our function. Suppose it was defined from minus pi to pi by some graph like this, right? We just repeat that graph after every 2 pi, so that the function is defined for all real numbers, right? Then it would be a function of period 2 pi, and it would be defined for all real numbers. And there is a slight problem, of course, at these endpoints, but they won't affect us, because finitely many points won't affect us in the evaluation of the integral, because we will have to make a choice at these points, 3 pi, 2 pi, plus minus 3 pi, minus 5 pi, whether we want to choose the endpoint of the preceding part of the graph or the beginning of the next portion of the curve. So it is the same thing as saying we define f of x plus 2 pi to be f of x, so that this integral makes sense now after this substitution. Okay, so now we want to move ahead regarding the convergence of these integrals, not integrals, convergence of course, convergence of this integral, which would imply the convergence of Fourier series, because this is the expression for a more compact expression for the convergence of Fourier series, or the nth partial sum of Fourier series. Sorry, if this integral converges as n approaches infinity, then so must be the corresponding Fourier series. Okay, so now to get there we have to do quite a bit of work. To start with, we do this lemma that if an expression, in our case Snx, can be written as 1 by pi from x minus pi, that was our last formulation for this nth partial sum, f of x minus u dn of u du, then Sn at x is also equal to 1 by pi integral minus pi to pi f of x minus u dn of u du. And I can just take the integral from minus pi to pi. Okay, actually I can take any period of 2 pi basically. Okay, now from this we first now look at this function. The way now I have defined f is a function of period 2 pi. F is a function of period 2 pi, but so is dn, our Dirichlet's kernel. So therefore this whole expression, this integrand, is a function of period 2 pi. Now we show that for any function of period 2 pi, we show that now if g is any, now this whole function here is a function of period 2 pi, because both f and dn are functions of period 2 pi. We show if g is any function of period 2 pi, then of course I can write x minus pi to x plus pi gu du equal to minus pi to pi gu du. Now of course if I prove this is automatically proved, because it's more general, it's for any function of period 2 pi, and for our case this integrand is a function of period 2 pi. Okay, now what we do for this, we take this and show it is equal to this. Now I can write minus pi to pi gu du as minus pi to minus pi plus x g du plus minus pi plus x 2 pi g du. Okay, I just broke the integral into two. Let's call this I1 plus I2. Okay, now after that okay, now in next, now I1 let me write here, I1 is now the integral minus pi to pi plus x g du. Okay, now putting u equal to our variable of integration t minus 2 pi in 1 in I1, what do you get? First du would be the same thing as dt. Okay, now when u would be minus pi, when u would be minus pi, so t would be 2 pi minus pi, so that is pi. Similarly, when u would be equal to pi, so when u would be equal to pi plus x, then t would be 2 pi, u is now pi plus x, okay. Did I make a mistake? No. So what would be in terms of t? So now my new variable is t. When u would be equal to minus pi, you put here minus pi, you take this 2 pi here, so it would be pi. And how about when it would be minus pi plus x? Oh, there is the mistake. Okay, when it is minus pi plus x, you just put t would be, of course, 2 pi. You take this, okay, u is minus pi, you put minus pi here, whatever. So t is equal to 2 pi plus u, which would be 2 pi minus pi plus x, that is equal to pi plus x. So that I1 would be, our lower limit is of course pi to pi plus x g of t minus 2 pi dt, right? Now we know it's a but g is a function of period 2 pi. It is the same thing as pi to pi plus x of g of t dt, which is the same thing as pi to pi plus u pi plus x, sorry, gu du. Okay, now what I do, I just substituted back in this. I just substituted back here. So I would have minus pi. I mean this. I substitute I1 in this expression. So minus pi to pi gu du should be then equal to integral from pi to pi plus x gu du plus pi 2. That is integral from minus pi plus x. Okay, did I again make some mistake? No. Okay, here it should have been minus pi plus x to pi gu du. Now of course, now you just again mix, add the two integrals. So this is the same thing as you know, minus pi plus x to pi plus x gu du. So that's what we had to prove. That is our nth partial sum. Our this nth partial sum, we can write it in this form. Sn(x) is equal to 1 by pi x minus pi to x plus pi f of x minus u dnu du, where dn is the Dirichlet's kernel. Okay, now we want to move on. We have to do some preliminary work regarding the convergence of this integral, and we want to arrive at some sufficient conditions for the convergence of the Fourier series. And for that we need to do a few results before coming to what we call Dirichlet's kernel for the convergence of Dirichlet's criterion. Now we want to arrive at what we call Dirichlet's criterion for the convergence of Fourier series. But to get there, we need certain results. And to start with, let me go. To start with, let's do the starting theorem. We have to do certain theorems. That is, if f is bounded, rather if f is just integrable, by that I mean Lebesgue integrable in the interval. In the interval we now have taken to be minus pi to pi, and and an and bn are coefficients, or the Fourier coefficients. Fourier coefficients, that those integrals, we have done it now so many times, it has been repeated and repeated, and so I presume you know it. Then summation an square plus bn square, n runs from 1 to infinity, converges. This series converges if an and bn are Fourier coefficients. Now for that, we just look, it's very simple proof basically. We just prove it by, we know that the integral of a non-negative function is again non-negative, so 0 would always be less than equal to minus pi to pi f minus summation k runs from 1 to n ak cos kx plus bk sin kx squared dx. So this would always be non-negative. We just expand this integrand, and I write it as minus pi to pi f square dx plus minus pi to pi summation k runs from 1 to n ak cos kx plus bk sin kx whole square. Now I mean to say I write it as a minus b whole square is a square plus b square minus 2ab minus twice summation k runs from 1 to n ak integral minus pi to pi f cos kx plus of course dx plus bk minus pi to pi. I've got a square b square, of course I should have f sine kx dx, right? Okay, so summation runs over here. Now look at this. Now before taking this into consideration, let's look what we have here. Now I know that what is ak? ak is minus, ak is basically 1 by pi minus pi to pi fx cos kx dx, right? So that means minus pi to pi fx cos of kx dx is basically pi into ak. So that means this integral is basically pi into a sub k. Similarly, this integral is nothing but pi into p sub k. So that means this expression. Now keeping this as it is, so this would be of course integral minus pi to pi f square dx, right? Then I have whatever this is minus pi to pi summation this square dx, but this has been simplified. It will be simply minus 2 pi summation now ak square plus bk square. K runs from 1 to n. So this is really simplified. Now do work it out at home. Okay. Keeping it there. Now let's look at this term. Minus pi to pi summation k runs from 1 to n a sub k cos kx plus b sub k sin kx square dx, right? So this can be basically written as this is minus pi to pi summation. I can just put the summation inside, so that would be okay, actually square is above it, huh? Because it is a square plus b square minus 2ab. The square is over the summation. So if I expand the sum inside, it would be basically a1 cos x plus b1 sin x plus a2 cos 2x plus b2 sin 2x plus so on and so forth, plus up to an cos nx plus bn sin nx. Because it is squared, so I multiply it again. So we would have a1 cos x plus b1 sin x plus a2 cos 2x plus b2 sin 2x plus so on and so forth, plus an cos nx plus bn sin nx dx. So it is this expression. Okay, after that, if I see what the products I get after multiplying them, I will either get cos x into cos x into sin x, no different integral multiples of x here. So it would be cos x into cos 2x, sin x into sin 2x, sin x into cos 2x. But as we already have in the beginning proved certain relations, that minus pi to pi cos kx cos nx, if these integers are different, then this would be 0, and this would be pi if n is not equal to k, and this would be of course pi if n is equal to k. Similarly, minus pi to pi sin kx sin nx would be 0 if n is not equal to k, would be equal to of course pi if n, n is equal to k, right? And of course minus pi to pi, the product cos kx, of course I mean integrating it, cos kx sine nx would be 0 in any case, whatever nk. Of course I'm talking about natural numbers, right? So this is going to be 0, this is going to be pi, this is going to be pi. That means when I multiply these two things, I'm doing the squaring, first taking the sum, then doing the multiplication itself, that is the same thing as square. The only thing that would remain is basically, cos x into sine x. Anything when they are different, whatever they are, cos kx, now this multiplied by this, when I integrate it, it would be 0. This multiplied by this, because cos x and cos x and 2x's, whenever they are different, it's again 0. Multiplying it with this would be again 0. So similarly with sine. So I would only have terms when I multiply a1 to a2, because this cos x and cos x, the sin x and sin x, similarly in that case I would get a pi when n is equal to k, means this cos something into cos something else is the same, the k and n are same here. So these terms I would get, and from these terms I would basically get, when I integrate them, firstly there would be a factor a1 into a1, b1 into b1. So basically I would get from this integral pi into a1 square plus b1 square plus a2 square plus b2 square. All other terms would be 0, an square plus bn square. So if I look at my expression, what I have got now, if I look at this expression, what I have got now, I need another page. Okay. If I look at this expression, what I have now is that 0 is less than equal to integral minus pi to pi. Where was I? Oh, yes. Oh, this. This is less than equal to, I'm in a hurry, I want to finish this because then I cannot upload it if it becomes longer. This thing, after you just look at it at home also, bk sine kx plus square dx, this is always non-negative, of course whole square, so it comes to be equal to minus pi to pi, of course f square dx. Then I have minus pi summation, plus pi ak square bk square, just check it, k runs from n to n, then minus 2 pi summation k runs from 1 to n ak square bk square. Okay, of course, so that would give me that I would get it from it that summation k runs from 1 to n, this would imply ak square bk square is less than or equal to, I just transpose it to this, minus pi to pi f square dx. Now this is true for all n, and since f belongs to Lebesgue integrable functions on minus 1 by 2, it implies that f square also belongs to Lebesgue integrable functions from minus pi to pi. So which means that this would be less than infinity, whatever the n. So it would be a finite thing. So therefore, letting n approach infinity in the left hand side, because the right hand side does not depend upon n, we get summation n runs from 1 to infinity an square plus bn square converges, which would imply that an square plus bn square would converge to 0 as n approaches infinity, which you already know, which would imply that an and bn both must converge to 0 as n approaches infinity. So from this we get that if if f is a Lebesgue integrable function, then its Fourier coefficients must converge to 0. So that gives us something to ponder upon, and you clearly know that it is one of the necessary conditions for the convergence of the seed, but it is not sufficient. But we are going to look at the sufficient conditions for the convergence of the Fourier series. Let me stop it here.